Alright, let's go. Number 10. The Kessler Syndrome Cascade. On February 10, 2009, an inactive Russian satellite collided with an American Iridium communications satellite 490 miles above Siberia. The collision between Iridium-33 and Cosmos 2251 created over 2,300 trackable fragments, each traveling at 17,500 miles per hour, 10 times faster than a bullet. This wasn't just another piece of space junk. It was confirmation that a theoretical nightmare had become reality. In 1978, NASA scientist Donald J. Kessler published a paper predicting that orbital debris would eventually reach a critical density where collisions would become self-sustaining. Each impact would create exponentially more fragments, triggering a cascade of destruction that would render Earth orbit unusable for generations. The scientific community took note, but the prediction seemed distant, theoretical, something to worry about in the far future. The 2009 collision proved Kessler catastrophically correct. Today, the Space Surveillance Network tracks over 34,000 objects, larger than 10 centimeters in orbit around Earth. But that's just what we can see. An estimated 130 million pieces of debris smaller than 1 centimeter are circling the planet right now, each one invisible to our tracking systems, but lethal to any spacecraft they strike. The cascade is already happening. What makes this particularly terrifying is the threshold we've crossed. Atmospheric drag naturally removes some debris over time, but recent analysis suggests collisions are now generating fragments faster than the atmosphere can clean them up. The process has become self-sustaining. Each day, the probability of catastrophic collision increases. We've built our modern civilization on satellites we can no longer protect. GPS, communications, weather forecasting, military defense, all dependent on orbital infrastructure that exists in an increasingly hostile debris field of our own creation. The question isn't whether the cascade will accelerate, but whether we'll recognize the tipping point before our connection to space shatters permanently. Number 9. The Andromeda Milky Way collision. In 2012, astronomers using the Hubble Space Telescope confirmed what theoretical models had long predicted. The Andromeda galaxy is rushing toward us at 250,000 miles per hour. The collision is inevitable. Using precise measurements of Andromeda's motion across the sky, NASA scientists calculated the appointment written into the fabric of space-time itself. For decades, astronomers knew Andromeda was approaching based on its blue shift, light waves compressed by the galaxy's movement toward us, but they couldn't determine whether it would collide with the Milky Way or pass harmlessly nearby. The 2012 Hubble observations measured Andromeda's sideways motion with unprecedented precision, removing all doubt. These two spiral galaxies, separated by 2.5 million light-years, are on a collision course. The merger will begin in approximately 4 billion years. Andromeda contains 1 trillion stars, compared to our Milky Way's 200 to 400 billion. When they collide, the gravitational chaos will be extraordinary. While individual stellar collisions are unlikely due to the vast distances between stars, the interaction will reshape both galaxies completely. Stars will be flung into new orbits. Some will be ejected into intergalactic space. Others will plunge toward the merging galactic cores. Our solar system faces uncertain fate. Computer simulations suggest the Sun has roughly a 50% chance of being pushed into a wider orbit, farther from the galactic center. There's a smaller but non-zero probability that we could be ejected from the merged galaxy entirely, cast adrift in the darkness between galactic superclusters. In the worst-case scenario, gravitational interactions could hurl Earth toward one of the supermassive black holes at the galaxy's centers. The collision will create a new elliptical galaxy that astronomers have already nicknamed Milky. Any civilizations existing at that time will witness a sky transformation beyond imagination. Two galaxies tearing each other apart over hundreds of millions of years, creating stellar nurseries and gravitational destruction on an unprecedented scale. The appointment has already been made, and there's nothing any future civilization could do to cancel it. Number 8. The Rogue Planet. In 2011, astronomers working with the MOA collaboration made a discovery that challenged our understanding of planetary systems. Planets drifting through interstellar space with no parent star. These rogue planets were ejected from their solar systems by gravitational interactions, now wandering the galaxy in absolute darkness and cold. The discovery was revolutionary, but the implications were unsettling. Planets are supposed to orbit stars. That's the fundamental structure of solar systems. But gravitational simulations of planetary formation revealed an uncomfortable truth. During the chaotic early years of solar system development, planetary ejections are common. For every stable solar system like ours, multiple planets were likely hurled into the void. The 2011 discovery confirmed what the mathematics predicted. The galaxy is filled with orphaned worlds. Conservative estimates suggest there are approximately 2 billion rogue planets in the Milky Way, more planets than stars. These dark worlds drift through space at typical galactic velocities around 30 kilometers per second. Their surfaces frozen at temperatures near absolute zero zero. They emit no light. They're detectable only through gravitational microlensing, the brief brightening of a distant star when a massive object passes in front of it. Some of these rogues may be Jupiter-sized or larger. We have no way to detect a rogue planet entering our solar system until it's already here. Unlike asteroids that orbit the sun and follow predictable paths, a rogue arrives from interstellar space on a trajectory we couldn't have anticipated. Its gravitational influence could destabilize planetary orbits, eject Earth from the habitable zone, or send the asteroid belt into chaos. Computer models showed that a Jupiter-mass rogue passing through the inner solar system would reshape everything. The terrifying reality is the combination of numbers and invisibility. 2 billion dark planets wandering the galaxy. Any one of them could be heading toward us right now, traveling at 67,000 miles per hour through the void. We wouldn't see it coming. We'd detect its gravitational effects only when it was already pulling on the outer planets, and by then we'd have months at most to prepare for a planet-sized object tearing our solar system apart. Number 7. The Betelgeuse Supernova. Betelgeuse, the brilliant red star marking Orion's shoulder, is dying. This red supergiant, approximately 650 light-years from Earth, has already begun its death throes. In late 2019, astronomers watched as it dimmed by an unprecedented 35%, a behavior that suggested it might explode as a supernova within our lifetime. The astronomical community erupted with excitement and concern. Red supergiants like Betelgeuse are stellar monsters. Betelgeuse measures roughly 700 times larger than our Sun. At approximately 10 million years old, it has exhausted most of its nuclear fuel and exists in an unstable state, fusing heavier and heavier elements in its core. The laws of stellar evolution are absolute. When a star this massive runs out of fuel, it collapses catastrophically and rebounds in a supernova explosion. For Betelgeuse, that moment could arrive tomorrow or in 100,000 years. The December 2019 dimming event captivated astronomers worldwide. Some speculated it might be the beginning of the end, the outer layers becoming unstable before collapse. Others suggested it was a massive ejection of stellar material obscuring the star's light. Subsequent observations revealed an enormous dust cloud. But the question remained, was this normal red supergiant behavior or the prelude to detonation? When Betelgeuse explodes, it will become a Type 2P supernova, briefly outshining the full moon and remaining visible in daylight for weeks or months. The neutrino burst will arrive hours before the visible light, particles streaming through Earth at near light speed detectable by neutrino observatories. But the real concern is what comes after. Recent models suggest the explosion will emit a burst of gamma radiation and high-energy particles that, even from 650 light-years away, could partially strip Earth's ozone layer. The light we see from Betelgeuse left that star 650 years ago. It might have already exploded. The deadly wavefront could be racing toward us through the dark right now, and we won't know until the sky suddenly ignites with the death scream of a star. We exist in a state of cosmic uncertainty, unsure whether we're watching a living star or the ghost of one already gone. Number 6. Magnetar SGR 180620. On December 27, 2004, at 21:30 UTC, Earth's magnetosphere was struck by the most powerful burst of energy ever recorded from beyond our solar system. In 1/10 of a second, a stellar object 50,000 light-years away released more energy than the Sun produces in 150,000 years. Satellites were temporarily disabled. The ionosphere was visibly disrupted. Aurora appeared at unusual latitudes. Something had reached across the galaxy and touched us. The source was identified as SGR 180620, a magnetar, a type of neutron star with a magnetic field so powerful it defies comprehension. With a magnetic field strength of approximately 10 to the 15th power Gauss, magnetars possess the strongest magnetic fields in the known universe. For comparison, Earth's magnetic field measures about 0.5 Gauss. A magnetar's field is so intense that within 1,000 kilometers, it would distort the electron clouds of atoms, making chemistry impossible. The December 2004 eruption was a starquake, a sudden fracture in the magnetar's crust, releasing an explosive reconfiguration of its magnetic field. The resulting gamma-ray and X-ray burst traveled across 50,000 light-years and still arrived with enough energy to measurably affect Earth's upper atmosphere. Scientists calculated that if this event had originated from a magnetar just 10 light-years away, the radiation would have been lethal to most life on Earth's surface. Only about 12 magnetars are currently known in our galaxy, but that's surely an incomplete count. These objects are small, typically just 20 kilometers in diameter, and only detectable when they erupt. Dormant giant magnetars could exist much closer to Earth, invisible and silent until a starquake triggers an eruption. The 2004 event demonstrated they don't need to be nearby to be dangerous. From halfway across the galaxy, SGR 180620 proved that magnetars can reach us. How many magnetars lie hidden in our cosmic neighborhood, their magnetic fields coiled like loaded springs, ready to release an eruption that would reach us faster than we could comprehend what was happening? If a magnetar within 10 light years erupted with the intensity of the 2004 event, we'd have roughly 10 years of warning, the time it takes light to travel that distance. But that light would carry not a message of the coming danger, but the danger itself, arriving simultaneously with the news that we're already too late. Number 5. The Carrington Event 2.0. On September 1st, 1859, British astronomer Richard Carrington was sketching sunspots when he witnessed something unprecedented, a massive solar flare erupting from the sun's surface, visible in white light through his telescope. Carrington immediately understood he was observing something extraordinary. 17 hours later, the fastest coronal mass ejection ever recorded slammed into Earth's magnetic field with devastating force. Telegraph systems worldwide exploded in showers of sparks, shocking operators and setting offices on fire. Some telegraph lines continued operating even after being disconnected from their batteries, powered solely by the electrical currents induced by the geomagnetic storm. Aurora Borealis appeared as far south as the Caribbean, so bright that people in the Rocky Mountains woke at night thinking it was dawn. The event, now called the Carrington Event, represents the most powerful geomagnetic storm in recorded history, with an estimated intensity of minus 1,760 nanoteslas. Our technology-dependent civilization is catastrophically more vulnerable than 1859's simple telegraph networks. In 2008, the National Academy of Sciences published a report estimating that a Carrington-level event today would cause approximately $2.6 trillion in damage to global infrastructure. Power grid transformers, which require 18 months or more to manufacture and replace, would be permanently destroyed by the induced electrical currents. Satellites would be disabled by radiation. GPS would fail. Communications networks would collapse. We nearly experienced this catastrophe in July 2012. A coronal mass ejection of comparable magnitude to the Carrington event erupted from the sun and tore through Earth's orbit. It missed us by 9 days, the time it took for Earth to move to where the CME had been. NASA scientists analyzing the 2012 event confirmed it possessed sufficient intensity to cripple modern technological civilization. We were saved by cosmic timing, nothing more. The probability of a Carrington-level event is estimated at 10 to 12% per decade. We've been fortunate for over 160 years, but the mathematics are absolute. The sun doesn't know we've built a civilization that would collapse in darkness without its cooperation, and it has no reason to care. When the next great solar storm erupts, we'll have perhaps 15 minutes of warning before the planet goes dark. Number 4. Sagittarius A Star Awakening. At the center of our galaxy, 26,000 light-years away, lurks a supermassive black hole containing 4.15 million solar masses. For decades, Sagittarius A Star appeared relatively quiet, a dormant monster at the heart of the Milky Way. Then, on May 13th, 2019, astronomers observing with the Keck telescope in Hawaii witnessed something that had never been seen before. Sagittarius A Star suddenly flared to 75 times its normal brightness in near-infrared wavelengths. Supermassive black holes at galactic centers exist in two states, active and dormant. Active galactic nuclei emit enormous jets of radiation and particles as they consume matter, outshining all the stars in their galaxy combined. Dormant black holes like Sagittarius A Star sit quietly, only occasionally flickering as small amounts of material fall past the event horizon. The May 2019 flare was unprecedented in decades of observation, lasting several hours before fading back to normal levels. What makes this deeply unsettling is the evidence that Sagittarius A Star wasn't always dormant. The Fermi bubbles, enormous lobes of gamma-ray emission extending 25,000 light-years above and below the galactic center, suggest a massive eruption occurred sometime in the past few million years. X-ray echo observations of molecular clouds near the galactic center show evidence of intense radiation just 100 to 200 years ago. The black hole has a history of violent activity. If Sagittarius A Star enters a sustained active phase, it could emit jets of radiation and high-energy particles directly along the galactic plane, where Earth resides. We orbit at a distance of 26,000 light-years, but we're positioned in the potential danger zone. The radiation intensity would be 26,000 times stronger than the cosmic background by the time it reached us. While not immediately lethal, sustained exposure over decades could strip portions of our atmosphere and drastically increase surface radiation levels. The monster at the heart of our galaxy has been sleeping for millennia, but the May 2019 flare might be the first stirring of something ancient and hungry. We're trapped in orbit around it with nowhere to run, watching for signs signs that it's waking up, knowing that any activity we observe already happened 26,000 years ago when the light began its journey to us. Number 3, 99942 Apophis. On December 21st, 2004, astronomers at Kitt Peak National Observatory in Arizona discovered an asteroid that would briefly achieve the highest impact probability ever assigned to a near-Earth object. Within days, 99942 Apophis had been calculated to have a 2.7% chance of striking Earth on April 13th, 2029. For the first time in history, an asteroid reached level 4 on the Torino Impact Hazard Scale, a rating reserved for objects posing a genuine threat requiring government attention. Asteroids are supposed to be predictable. We track their orbits, calculate their trajectories decades in advance, and the mathematics tell us whether they're dangerous. But Apophis presented a unique problem. This 370-meter wide asteroid would make an extraordinarily close approach to Earth in 2029, passing just 31,000 kilometers from our surface, closer than geosynchronous satellites. That close approach would dramatically alter its orbit through gravitational interaction with Earth. Further calculations revealed something more disturbing. The 2029 flyby will pass Apophis through a gravitational keyhole, a precise region of space just 600 meters wide. If the asteroid passes through this keyhole, Earth's gravity will alter its trajectory in exactly the right way to guarantee an impact on a subsequent orbital pass in 2036. Scientists won't know if Apophis threads the keyhole until after it passes in 2029. If it does, we'll have exactly 7 years to prepare for certain collision. An Apophis impact would release approximately 1,200 megatons of energy, equivalent to 80,000 Hiroshima bombs. If it struck an ocean, the resulting tsunami would devastate coastlines across an entire hemisphere. A land impact would create a crater several kilometers wide and trigger earthquakes detectable globally. The asteroid is large enough to cause regional devastation and global climate disruption from ejected debris, but not large enough to cause mass extinction. On April 13th, 2029, you'll be able to see Apophis with the naked eye as it screams past Earth at 30,000 kilometers, closer than our satellites. Will you be watching humanity's near miss, or the preview of an appointment we cannot break 7 years later? The mathematics of orbital mechanics are absolute and the keyhole is waiting. Number 2, Wolf-Rayet 104 gamma ray burst. 8,000 light years from Earth in the constellation Sagittarius, 2 massive stars orbit each other in a cosmic dance of death. One of them, WR104, is a Wolf-Rayet star containing 25 solar masses in the final stages of its life. When it explodes, and it will explode soon on cosmic timescales, it will likely produce a gamma ray burst. Observations suggest its rotational axis may be pointed directly at Earth. Wolf-Rayet stars are among the most massive and unstable objects in the universe. They've shed their outer hydrogen layers through powerful stellar winds, exposing the helium and heavier elements being fused in their cores. WR104 orbits a companion star every 220 days, and this orbital motion creates a spectacular pinwheel pattern of dust and gas visible in infrared observations. The pinwheel's geometry has allowed astronomers to estimate the star's rotational axis, and the results are deeply concerning. When massive stars like WR104 explode, they don't radiate energy equally in all directions. Instead, they produce focused beams of gamma radiation along their rotational axes, beams typically just 2 to 20 degrees wide, but containing energy equivalent to a supernova's total output. These gamma ray bursts are the most energetic events in the universe after the Big Bang. Observations of WR104's orientation suggest uncertainty of approximately plus or minus 30 degrees. We might be in the beam's path. We might not. The margins are too close for comfort. If WR104's beam hits Earth when it explodes, the initial gamma ray pulse would strip half our ozone layer in seconds. The radiation would be 10,000 times more intense than a solar flare. Ultraviolet radiation would then flood the surface, causing immediate damage to DNA and killing phytoplankton, the foundation of the ocean food chain. Within months, the global ecosystem would begin collapsing. We would have zero warning. The explosion's light and the killing burst would arrive simultaneously. 8,000 years ago, when humans were just beginning to farm the first crops, WR104 might have already exploded. The light-carrying news of that death, and the invisible beam that could end everything we've built, may be crossing the final light years of space right now. We exist in the space between those possibilities with no way to know which timeline we occupy until the moment the universe decides to inform us. Number 1. The false vacuum collapse. In 1980, physicists Sidney Coleman and Frank DeLucia published a paper in Physical Review D that revealed something terrifying about the nature of reality. The universe might not be in its lowest energy state. Like a pencil balanced balanced on its tip, the fabric of space-time itself could be metastable, one quantum fluctuation away from catastrophically transitioning to true stability. The physics are sound, the mathematics are rigorous. The implications are existentially devastating. At the heart of this scenario is the Higgs field, the quantum field that gives fundamental particles their mass. When physicists at CERN discovered the Higgs boson on July 4th, 2012, they measured its mass at 125 gigaelectron volts. This measurement allowed theoretical physicists to calculate whether our universe exists in a stable configuration or a metastable false vacuum state. The calculations revealed we exist at the boundary between stability and metastability. The universe isn't sitting at the bottom of an energy well. It's perched on a ledge. If the Higgs field exists in a false vacuum state, a random quantum fluctuation anywhere in the universe could trigger collapse to the true vacuum. A bubble of true vacuum would nucleate at some point in spacetime and begin expanding at the speed of light. Inside this bubble, the fundamental constants of physics would be different. The forces that hold atoms together would change. Matter as we know it couldn't exist. The bubble wall would rewrite reality itself as it expanded, and there would be no escape. You can't outrun something traveling at the speed of light. What makes this particularly horrifying is the absolute nature of the threat. You wouldn't feel it. You wouldn't see it coming. The bubble wall would arrive at 670 million miles per hour, and your atoms would simply cease to function before your neurons could register anything was wrong. There would be no warning because the information that the collapse had occurred would travel at the same speed as the collapse itself. The discovery and the annihilation would be simultaneous. The probability of false vacuum collapse is impossible to calculate with current physics, but it's non-zero. Every quantum fluctuation in the universe is a dice roll against the void. The collapse could happen in the next billion years, the next 1,000 years, or in the fraction of a second it takes you to finish reading this sentence. The 2012 CERN measurements placed us in the metastable region, meaning this isn't theoretical speculation. It's a genuine physical possibility grounded in our best understanding of particle physics. We exist in the moment before we discover whether the universe's foundations are real, or whether we've been living in a house of cards that's already begun to fall. The collapse might have already occurred a century ago in a distant galaxy, the bubble wall racing toward us at the speed of light, erasing reality light year by light year. We wouldn't know until it arrived, rewriting the laws of physics that make our existence possible, transforming everything we are and everything we've ever known into a configuration of space-time where consciousness, matter, and meaning simply cannot exist. If you want to see more videos like this, click the video on screen now and make sure to subscribe.